Hey guys, so let's start with this example here, and we're asking to identify the the magnetic flux through the loops. So basically, just quick reminder. So the formula that we use to identify the magnetic flux, it is phi area times magnetic field and cosine theta. So we have the loop, so it is by r squared times magnetic field times cosine theta. So now the only thing I'm concerned, I wanted to find the magnetic or the angle between my axis and magnetic field. So magnetic field is going into the page, and if we draw the line of the axis, so even the magnetic field point out of the page is in different different plane, but still you find the theta or the angle, it's 90 degrees. So from here, it is magnetic form flux times R, which we had the value, times P times cosine 90 degrees. So there is no flux going through this one, which obviously because they are the magnetic field and the rho, they are in the same, they are the same plane. So you can see just pointed the same plane. So there is no intersections. So there is no rotation, there is no flux. So let's see some more example regarding to how to calculate the magnetic flux based in the based in the loop and the angle and the magnetic field. So in this equation, asks you to rank the magnetic flux through each loop. So here is the unit based in meters. So all the units here is the meter. So what, and the magnetic field by Tesla. So the formula is straightforward. As we saw it before, the first time, let's go for the first one here. We need to find the axis. So the axis, the point here is the point through, go in and out of the page. That's the axis. And it would be pointed at the same direction of magnetic field. So the phi or the angle theta will be 0. And that situation is here. It's valid for the other cases too. So let's go the phi number 1, or the magnetic flux for the loop number 1, which basically the A times B times cosine theta, which this time it is 0. So we can forget right now, cosine 0 is 1. So just basically the area times magnetic field. So let's see, I'm fine. The area for the first one here is 2 times 2 will be 4 meter squared times 1 Tesla. So I have here 4 Weber. So the first one, 4 Weber as the magnitude of the magnetic flux. Let's see for the second loop, phi 2. Even I have the magnetic field, it is now, right now it is 2, and the area of the loop is 1 by 1. So still 1 meters. Sorry, 1 meter times 1 meter times 2 Tesla. So in this case, give me 2 Weber. So even the magnetic field is increased, but the area is decreased. So I end up with the less magnitude or the magnetic flux. Let's go for the third one, which is a little bit kind of the confusing in this case here. We have, here is the area, but the area is divided 2 parts. So the first part, the magnetic field point out, the second part, the magnetic field point in. So basically we have, here is the 1 meters, and here is the 1 meters, and this one is 1 meter. Okay, so here is the point out, the page. So the magnetic field will be in the first part, on the first loop, 1 meters times 1 meter times 1 Tesla, where this area here out of the page. from the first part. Now the second part, which is goes from the opposite directions, so we can describe that the opposite by negative sign. So we have the same area, 1 meters times 1 meter times 1 Tesla. And where is this part here? Into the page. So basically they are cancel each other. So I end up with here is the 0 Weber in that case. So let's move for the last figures that we have. Loop 4, phi still 0. Now the only thing I want to focus about it, the magnetic field, it has just certain area, but not all the area, just the half. So as we mentioned before, we are focusing just in the area where we have magnetic field. So here is the 1 meter in that case, times 1 meter in that case. So we end up with the area, it will be 1 meters times 1 meters times 2 Tesla. And we end up with the 2 Weber. Now I can rank my my magnetic flux. So it seems to be the phi 1 is the largest, larger than phi 2 equal phi 4 and larger than phi 3. So let's see the second example here. It's not the regular shape that we did before. Now we have the circulars and we have small rectangulars here where magnetic field point into the page and ask to find the magnetic field through the loop. Okay. So again, we are focusing just the area. This is the area I want to find. It's basically the rectangular area. That's my area I am focused about. Not about the circle, there is no magnetic field in it. So in that case, we just straightforward, here is the phi, magnetic flux, area, times magnetic field, times cosine theta. What about the theta? That's in this case here, the same directions, point in and out of the base, the same direction of magnetic field, so the theta equals 0. So what we end up A times B, again, we don't about the circular, about the area of the magnetic field. A times B, rectangular area, times magnetic field, times cosine 0 degree. Now I plug my numbers, my A and B, my H, 0.1 meters, times 0.15 meters, times my magnetic field 0.45 Tesla. Sorry about that. And this number here seems to be 6.8 power to the minus 3 Weber. What about the directions? Into the page. The same direction of magnetic field. Now let's see this example here, just to go back to when we started in chapter 25, try to find the induced current. And now you can say, okay, I'm looking for the induced current, why I am looking for the flux. So let's see here, before next lecture, we're gonna find the connection between induced current and flux. But now let's see now what the area and how we can calculate, because that's for the magnetic flux through the loop formed by the rod and rails. So here is the rod and rails, and there are flux has been created between those. So in that case, this is the initial case, and this is the final case. And in the case here, is it true there is the flux comes through here, but in our case, we're looking for the induced, we are looking for the closed loop, which in this case, this loop here. And this one in the second or the final one, this loop here. That's the loop we are concerned about. We want to find the flux in those two loops. So here is the first part, initial. Let's call it phi I. Again, area times B and times cosine theta. What about the theta? In this case, as we previous example, we solve it. The theta will be in the centers, so it's going to be the same one. So the theta equals 0. 0 degree theta in that case. Now let's go back to plug the numbers. For the A, I have 25 centimeters times 25 centimeters. Here is the 0.25 meter square times the magnetic field will be 1.4 Tesla times 1, it will be the same value. So as a result, 8.8 power to the minus 3, 8.8 power to the minus 3 Weber. And regarding for the direction, into the page. Let's see about the second one, the final one. Here is the final. We have the phi, it is called final. Similarly for this one, it is A times B times cosine 0. So I have A in this case, I have 5 centimeters times 25. So here is the 0.01 meters times 0.25 meters times 1.4 Tesla. So in this one here, you end up with the 1.8 power to the minus 3 Weber. And the same thing into the page, the same direction. So now what we observe, this decrease or increase, we observe the magnetic flux in the initial value is larger than the final one. So the phi is decrease. So so next lecture, we're gonna write or define the connection between induced current and magnetic flux. Okay, thank you guys. And this is the end of this video and this lecture too. Thanks.